Welcome to Super Easy Physics and Mathematics, CPAM. The aim of this YouTube channel is to make the learning of physics and mathematics easy and fun for every student.
Subscribe and we will help you to easily upgrade your performance to an A+.
So, this paper had the duration of 1 hour and you are expected to answer 4 questions. Okay, you are going to plot one graph and you are going to plan one practical. Question 4 is planning of investigation. Then between question 1 and 3, you have plotting of graph, handling of experimental data. Okay, so let's see. Let's go. Question 1. Okay, we are looking at moment of a force. So, but you are balancing a meter rule with load using 2 springs. A student investigates the force supporting a meter rule. He used the apparatus shown in figure 1. The scale of the meter rule faces upward, so you can read it. So you have a string. So the distance of the load from the edge is D. So we have the loop of the rule. So, okay. Now let's see. A student ensures that the meter rule is horizontal. Briefly describe how to check that the rule is horizontal. You must draw a diagram if it helps to explain your answer. So, I measure equal distance between the horizontal ruler and the bench at the 2 positions where the loop of the thread hold the meter, hold the ruler. Or I use a set square to check the balance between the ruler and the stand, the retor stand. So if you want to check that the angle 90 is equal, so that is easy. The student set up the distance between 0 cm mark and the 1 Newton load as shown. He moved the thread supporting the 1 Newton load so that it is at the mark on the meter rule shown. So this is the loop. Now, record the distance D. So all you need to do, you read this distance, which is 5.2 cm. The unit is already given, so you don't need to write it. The reading on Newton meter P and Newton meter Q are shown. Now record FP, the reading on Newton meter P, and record FQ, the reading meter on meter Q. So you just read this value and write it down here. Read this value and write it down here. So let's read the first one and then the second one. Write it down there. Okay, the student moved the 1 Newton load to the distance D equals to 25, D 35, 45, and so on. Now, he reads the value Fp on Newton and the value Fq in Newton. His reading are shown on this table. So you have the distance, you have the force or the force meter Fp, you have the force meter reading Fq here. Now using the value from table 1.1, plot a graph of Fp in Newton on the vertical axis against D on the x-axis, and on the same axis using the same scale, plot a graph of Fq in Newton on the vertical axis against D S on the horizontal axis. So draw 2 lines of best fit, one for each set of plots. Show clearly on your graph which line is for Fp and which line is for FQ. So we are plotting two straight lines on this graph. So this is the graph paper given to you. Okay. Now, you were not told to start from any place, so you will use your initiative. So D is on the horizontal axis. So let's label our axis. So FPFQ is already written there for you. Okay. So here, you are plotting your horizontal axis labeled. So let's do the calibration. Since I was not told to start from origin, I decide to spread it out like this. So I start from 20. Since the maximum, the lowest value is 25 to 65. So I'm putting it from 20 to 70. So now the force is ranging from 1.3 to 1.8. So, and then this one is ranging from 1.6 to 1.9. So once I have my value, so I can start from 1 to 2. 1 to 2 for both of them. So I start from 1.1, okay. Since the lowest value, 1.3, I have 1.6. So I'm starting from 1.1 to 2 points. So 1.1 to here, I have 1.3, 1.5, 1.7, 1.9, 2.1. So each of these gap, 10 cm, is 0.2. So each one is 0.1, 0.2, 0. So that is what I'm doing. Okay. So let's see. Let's plot the graph now. I first of all plot for P. Oh, okay. Let's plot for Q. So I have that. Then I'll draw the line of best fit. That is for FQ. Now I will draw for FP. Draw the line of best fit. All right. Where did the two lines intersect? At 50. So I have that. From your graph, determine F0, the value of FP where the two lines of best fit cross. So you have that. So you look for your F0, which is about 5.51 Newton. So from that value, so I'll write it here. So which is where the two lines cross, I just read it to the F, which is my F0. Now, from your graph, determine F0, the value where the two lines of best fit cross. We have already done that. Calculate the weight WR of the meter rule using the equation. So we're to use this equation. WR is equal to 2 times F0, take away K, where K is equal to 1 Newton. So you just substitute. So which is what? 2.02 Newton. So the correct range for your value based on this examination, your value must lie between 0.18 and 2.2 Newton. So this is the range of value that is correct. So what we have here is 2.02 Newton. So you have your 2 mark. Now, another student does the experiment with the same equipment. He reads the value of FP, which are the same as in table, but the value of FQ are all 0.1 greater than those in the table. Suggest a reason for this difference. Assume that the value in the table 1.1 are correct. So what happened? Transferred error. The first meter Q has a 0 error of 0.1 Newton. Or the first meter Q was not set to 0 at the start of the experiment. So the student was transferring the error, the reading. Okay. Now question 2. A student investigates how the volume of water affects the rate at which water in the beaker cools. Okay, he used the apparatus shown in figure 2.1. So you have a beaker, you have the thermometer, then the bench. So this, you have this thermometer reading. So now record the room temperature shown in the thermometer. So this is the value. So if you read that, which is 19 degrees Celsius. Describe one precaution that should be taken to ensure that the temperature reading in the experiment are as accurate as possible. I set my eye or sight perpendicular to the scale of the thermometer. Okay, I take reading when the mercury stops rising. It's not when it is still rising. The student pour a volume of 150 cm cube of water into the beaker and record the temperature theta at time t0. She records the temperature of the water in the beaker every 30 seconds. She tips the water out and pour a volume of 50 cm cube of water into the beaker. The student repeats the temperature measurement for this volume of water. So the reading are shown in table 2.1. Now complete the heading. Time in second, unit of temperature, degree Celsius, degree Celsius. So it has two volume of water, 150 cm cube of hot water and 50 cm cube of hot water. So for you look at them, temperature reading for the two of them. Now write a conclusion stating how the volume of water affects the rate of cooling of water. Justify your answer by reference to the result. Now, when they say justify your answer, what the examiner expects you to do is that in your answer, you must make reference to the reading that you take from this table. Okay, so let's see how we answer a question that has to do with justify. So now, what you need to do, calculate the higher the volume of water, the slower the rate of cooling. Okay, for the 150 cm cube, the temperature drop from 88 to 87.5 in 180 seconds. While the beaker with 50 cm cube, the water drop from 86 to 72 in 180 seconds. So you'll see the cooling rate. So I've made reference. Now, using the result for the 50 cm cube of water, calculate the average cooling rate X for the first 90 seconds of the experiment. Use the reading from table 2.1. So if you look at that, I have that. So I have this 0.1056 Celsius per second. Then another student does the experiment with the same starting temperature at the room with a much higher room temperature. State how this affects its value of X. Explain your answer with reference to the result for a beaker of 50 cm cube of hot water. Statement. The value of S will be lower than this. Explain. The temperature between the beaker and the room is less and the cooling rate will be lower. Okay. Some thermal energy is lost from the side of the beaker. the student wished to find out how much this loss of thermal energy affect the cooling rate of the 50 cm cube of water. Briefly describe an additional experiment that the student can carry out to investigate this. Explain how the result can be used to determine how much this loss affect the cooling rate. Additional experiments. So if you look at this, the student repeats the experiment with a lid on the 50 cm cube. So you want to control evaporation. Okay. Now, compare the cooling rate when the beaker is covered with lid with the value of S when the beaker was open. So that's how you use this result. With that, you pocket your 11 points. Question 3. Determine the focal length of a converging lens by different methods. Method 1, the student used the apparatus shown. A plane mirror, a convex lens, and then a source of light, and then the illuminated triangle. Okay, so now you can find the focal length, which is about 3.1 cm. The student set the distance between the illuminated and the mirror to 40 cm. He moved the lens until he sees a sharp image of the triangle in the card by the side of the illuminated object. Measure the focal length of the triangle. So we've done that. F1 equals to 3.1. Calculate the actual distance between the illuminated triangle and the lens in this experiment. This is a value for F1 of the lens. So you are given that the scale is drawn to 1/5 of the scale. 1/5 of the scale. So whatever you measure, so multiply by 5. So give me 5.5 cm. Briefly describe a technique to obtain an image on the card that is as sharp as possible in this experiment. Number 1, adjust the position of the lens slowly backward and forward until a sharp image is formed on the screen. Another student set up apparatus as shown above. You have this, put the lens, and then you get the sharp image on this way. So you get your U, and then from here you get your V. So you have the image distance. So here you have the object distance. So the student set up the distance between the illuminated triangle and the lens, U equals to 20. She moved the lens until a sharp image is formed. Then he measured H0, the height of the illuminated object as shown, H0. So you have H0, and then the height of the image. So if you do that, we see this. So the height of the illuminated object, which is what? 1.2 cm. So let's measure the height of the image. So you have like what? 5.1 cm. So 5.1 cm. All right. Now, describe one difficulty when measuring the height of the image in this type of experiment. Suggest an improvement to overcome this difficulty. Wow. So let's talk about the difficulty. Your hand gets in the way of the light. Okay? Now, so how do you improve it? Use screen with scale so you can easily read the height of the image directly from the screen, from the scale that is projected. So use translucent screen, and so you can measure its height from the back, from the rear. So if you use translucent screen, so you can measure the height of the image from the rear so that your hand will not block the ray of light forming the image. So calculate the value W using the equation. W is equal to H naught over Hi. So we have object distance over image distance, which is 0.035. Okay, calculate a second value F2 for the focal length of the lens using the equation. So you have U over W plus 1. So we get this. So which is what? 16.94. Okay, so approximately 16.2. Now, a student suggests that F1 and F2 should be equal. State whether the results support this suggestion. Justify your statement with reference to your result. The results support the suggestion. Justification. 5.5 and 16.2. Therefore, since 5.1 is approximately equal to Alright. So within the result support the suggestion, we have F1. So within, if you can easily approximate 15.5 to 16. Now, describe one precaution that should be taken to obtain reliable result for F1 and U in this experiment to measure the focal length and the object distance. I ensure that both the lens, the object, and the screen are perpendicular. Okay. I view the ruler perpendicularly to avoid error due to parallax. I repeat the reading and took the average value. So with that, you have your 11 marks. Let's go to the next question, question 4. A student investigates the resistance of a light-dependent resistor, LDR. The resistance of an LDR changes as the intensity of light falling on it varies. The resistance R of the LDR is calculated using the equation R is equal to V over I, where V is the potential difference across the LDR and I is the current in the LDR. Plan an experiment to investigate how the light intensity affects the resistance of an light-dependent resistor. The apparatus available include an LDR, equipment to connect the circuit, part of which is shown in figure 4.1, a lamp with a power supply. In your plan, you should complete the circuit diagram to show a voltmeter connected to measure the potential difference across the light-dependent resistor. State how the light intensity falling on the light-dependent resistor will be varied and list any additional apparatus needed. Explain briefly how to do the experiment, including any precaution taken to ensure reliable results. State one key variable to be kept constant. Draw a table or table with columns heading to show how to display the reading. You are not required to enter any reading in the table. Explain how to use the reading to reach a conclusion. So this is the diagram of the light-dependent resistor. You have the ammeter, you have the power supply. So let's get started. Now, what is the aim of this experiment? to investigate how the resistance of light-dependent resistor changes as intensity of light falling on it varies. Setup. I connect the voltmeter in parallel to measure the resistance across the LDR. So I put the switch, and then I put a light bulb at a distance of 30 centimeters away from the LDR. So distance of the lamp. So I can keep that distance constant. So let's say I connect the voltmeter in parallel to the LDR to measure the PD across it. I set the power supply at 6 volts and kept it constant throughout the investigation. I close the circuit and measure the initial current I and the initial voltage across the LDR without light falling on the lamp. I measure the distance L equals to 30 centimeters away from the LDR using the meter rule. Using the meter rule and position a lamp. I turn the lamp on and I measure the current I and V, and I calculate the resistance of the LDR. So I repeated that procedure. Then I set L as 40, so I'm changing the distance of the lamp from the light dependent resistor, 40 cm, 50 cm, 60 cm, 70 cm, and I measure the corresponding value of the current and PD in each case, and I calculate the resistance for each distance. Table of value. I have this distance of the lamp, then current, the voltage, then the resistance of LDR. Now, what are the independent variable? Distance of lamp, I'm testing for that. Then dependent variable, I have current, the PD, and the resistance of the LDR. So, analysis. I plot the graph of resistance on y-axis and distance L on s-axis. So I compare how the increase in distance affects the resistance from the value in the table and the line graph. So with that, we have come to the end of Physics Paper 6, Variant 3, May-June 2022. Thank you for your time. Thank you for reviewing this paper. You have learned some new strategy how to answer alternative to practical paper 6 question.
Subscribe and we will help you to easily upgrade your performance to an A+.
CPAM is the solution to better grades.